Log on, tune in, find out. Another good idea from Cambridge.
And he's going to talk on the L2 geometry of vortex moduli spaces.
Thank you very much. Thank you to the organisers for inviting me to participate in this programme. So this is really going to be a bit of light relief, I think, compared to most of the other talks I've been to here. It's very easy stuff, not very technical. I think everyone will be able to understand it, but I think it's quite pretty. Okay, so what we're studying is the L2 geometry of vortex moduli spaces. So the first thing to do is to define the moduli spaces that we're interested in. Okay, so to do some setup. Okay, so we're going to start off with a smooth complex line bundle over a surface which will either be a compact Riemann surface or possibly the complex plane with the Euclidean metric or with the hyperbolic metric. Okay, but the case we'll focus on mainly is compact Riemann surface. Okay, so we have a smooth complex line bundle over sigma, and we're going to give it a Hermitian fibre in a product. Okay, but we're not fixing a holomorphic structure on it. Okay, so if I'm given a section of this bundle, phi, and a unitary connection on that bundle, let's call it nabla, then there's a natural notion of what I mean by the energy of that pair, called the Ginzburg-Landau energy. So this originally comes from phenomenological theories of superconductivity, but it arises all over the place. It's a very interesting natural energy functional. So what is it? Well, it's half d nabla phi squared, where phi is my section, plus half the L2 norm squared of the curvature of my connection, plus 1/8 L2 norm squared of the difference of the length squared of my section from some parameter tau. Okay? So what do I say about this? Okay, so we have this real parameter tau, which we're going to take to be a positive number. Okay, so the interesting thing is to try and find critical points of that functional, and in particular, you really want to find the global minima of that functional. Okay, so I guess the first thing I should note is that there's an obvious huge symmetry group for this variational problem. So if I multiply, so if I define any smooth U1 valued function on sigma, then if I multiply my section by that function and I change my connection by subtracting off that imaginary form here, then it immediately follows from the definition that the energy doesn't change. Okay, so you have a huge infinite dimensional symmetry group, the gauge symmetry group. So, which I'll denote by curly script G. Okay, so this is the set of all sufficiently smooth maps from my Riemann surface to U1, where sufficiently smooth I'm going to be vague about. Depends what you want to use it for. Okay, so as I was saying, what we're really interested in is finding the global minimizers of that functional for a given bundle L. And the key to doing that is to use a trick which was noticed by Bogomolny in its simplest form way back in 1976. Although he certainly didn't write it in this language, it amounts to the same thing as he did. So he noticed that you could actually rewrite this Ginzburg-Landau energy in the following form. So you could take the 0,1 part of the differential of phi and add to it here, don't I? Yeah. That's squared, and half the integral over sigma of I times the curvature of your connection. And when you expand all this lot out and use some identities, it turns out that's precisely the same as the energy you started off with. Okay, so the interesting thing about that is that these two terms here are obviously non-negative, and this one here, well, I f nabla over 2 pi, its cohomology class is the Chern class. So this is a topologically invariant. This is just 2 pi times the degree of the line bundle. So you immediately get from this rewriting of the energy that the energy is bigger than, there's a tau missing there. Should be a tau there. You immediately get that the energy is bounded below by tau times pi times an integer n, where this is the degree of the line bundle. Okay, and furthermore, in order to attain that bound, both the non-negative terms in this decomposition must be exactly 0. Okay, so we have equality if and only if this pair of equations holds. Okay, so these are called the Bogomolny equations. Let me call them B1 and B2 for Bogomolny 1 and Bogomolny 2. And solutions of these are called n vortices. So an n vortex is going to be a solution of these. Okay, well, there's an immediate obstruction to solving these equations that you can find by integrating the second one over sigma. Okay, so if we integrate Bogomolny 2 over sigma, what do we get? Well, on the left-hand side, we just get 2 pi times the degree of the line bundle, and on the right-hand side, we get tau over 2 times the volume of my surface minus tau over 2 times the L2 norm squared of the section phi. So this is obviously non-negative, so this is less than or equal to this. Okay, so we see that you can only solve this if the volume of sigma is bigger than or equal to 4 pi n over tau. So this is called the Bradlow bound. Okay, so for the remainder of the talk, I'm going to assume that the Bradlow bound is it holds, so that we can actually find solutions to the theory. Okay, so n vortices are solutions of this pair of coupled first-order PDEs. What do we know about the existence of them? Well, that's a very well-studied problem. So it was first proved by Taubes in 1980 in the case where where I'm working over just the Euclidean plane. Then it was later proved for the compact case by Bradlow, and later still there was a different proof in the same case by Oscar Garcia Prada, which these are interesting. They use very different approaches to prove existence. Otherwise, I guess there wouldn't be any point of publishing that one. Okay, so I don't want to say anything much about that because that's not really the focus. I'm not really going to focus on how existence of solutions is proved. Let me tell you what the theorem is. So in all these cases, the theorem is as follows. Given an unordered set of n points, let's call them Z1 up to Zn in sigma, not necessarily all distinct. Then there exists an n-vortex, i.e. a solution of this pair of equations, with the Higgs field, so I call the section phi the Higgs field for reasons of, for historical reasons, I guess, with the Higgs field vanishing at the zeros and nowhere else, in fact. And furthermore, that solution is unique up to gauge. So of course, whenever you've got any solution, there's a huge infinite dimensional family of them. You just operate with this infinite dimensional gauge group. But modulo that action, the solutions are uniquely specified by the zeros of the Higgs field. Okay, so we're in this interesting situation where the moduli space topologically is very simple indeed, and everything you could possibly want to know about its topology is really known, I think. Okay, so the moduli space is the space where, so n is the degree of my Lamb bundle, or the vortex number. It's the space of n vortices modulo the action of the gauge group. And by the existence theorem of those, any one of those three versions of it, we know what this is, right? So it's just the space of unordered n tuples of points in sigma. So it's the symmetric n, it's the nth symmetric product of sigma. Sigma to the n divided by modulo the permutation group. Okay, so topologically it's very simple. Let's just have a couple of examples to keep in mind. So the really physically the most interesting situation is where the domain is the complex plane. Then we can always identify an n vortex. Remember, that's uniquely specified by an unordered list of n points in the complex plane. I can identify that with a unique monic polynomial whose zeros are those n points. I can then write that out, expand it out, and collect the coefficients, and identify this polynomial by the vector given by its coefficients. Okay, so in this case, the modular space is as simple as it could possibly be. It's just n-dimensional complex Euclidean space, topologically. Another interesting case where you can say very explicitly what the moduli space is the case where physical space is a two-sphere. So again, we can identify an n-vortex with a polynomial, but now we don't want to consider just monic polynomials because we want to think of the two spheres being the Riemann sphere, so the complex plane with a point out at infinity. So we need to account for the fact that some of the zeros might be at infinity. So we can identify it just with any old polynomial, not necessarily of degree n. Okay, and then we can, so again, the points are just the roots of this polynomial. And then we can identify that with its coefficients, except of course multiplying this polynomial through by a non-zero complex number doesn't change its roots. So I have to identify it with its projected equivalence class. So the space of n, the modular space of n vortices on a two-sphere is just CPM. Okay, so the point is the topology is well understood. One might almost say boring. So what is interesting? Why am I telling you about this? Well, the point is that it has an interesting geometry. Okay, and by geometry I really mean Riemannian geometry. It's quite hands-on stuff. Okay, so how can we naturally equip this moduli space with a Riemannian geometry? Well, one way is very high-powered and very elegant. You identify it as being zero set of a moment map, generating the gauge group action, and then use symplectic reduction to equip it with a canonical symplectic form and argue that that's compatible with a natural complex structure, and that way you get a Kähler structure. So that's very beautiful and elegant, but it's rather hard to get your hands on. So I'm going to define it's going to be the same geometry, it turns out, but I'm going to define it in rather more concrete terms. Okay, so what is a metric on Mn? Well, it's just an inner product in each tangent space, and it's enough to define the squared length of every tangent vector to Mn. So we have to think about what is a tangent vector. What is a tangent vector to Mn at the gauge orbit? Remember, this is a space of gauge orbits. At the gauge orbit of a particular n vortex, phi nabla. How should I think of that? Well, if I pick a particular representative from this gauge orbit, a particular solution of the Bogomolny equations, then I can really think of the tangent vector as being an infinitesimal deformation, okay, a variation of that. So what is that? Well, if I vary phi, that's a section of L, I get another section of L. So it's going to consist of a pair where epsilon is a section of L, and if I vary a connection, well, all connections differ from one another by one forms, imaginary one forms. So let me define the variation of nabla to be minus I times alpha, because then I've got a real form, which is convenient. So an infinitesimal variation of this pair you can think of as just being a section of the line bundle and a one form. And what does it mean to be tangent to the moduli space? Well, they'd better solve the linearized Bogomolny equations. So satisfying. So we have the Bogomolny equations. Have I read them off? There. So this pair must satisfy the linearization of the Bogomolny equations, which is the following. That and that. Okay, so let's call that LB1 and LB2, linearized Bogomolny equation 1, linearized Bogomolny equation 2. Well, that's not quite enough, because we don't really want to, what we would like is for this thing to be L2 orthogonal to the gauge orbit through phi nabla, right? So it's not enough just for them to satisfy this, because that would potentially give us a component which is just moving in the direction of the gauge group, okay, which isn't doing anything. So we should project it so that we should also insist that this thing here, this tangent vector, is orthogonal to the gauge orbit through this point phi nabla. And if we do that, it turns out that there's an extra condition. Which you can think of as Gauss's law, if you like to think physically. Okay, so tangent vectors are just pairs satisfying this triple of linear PDEs. And then once we've identified tangent vectors in that way, we can define the length to be just the obvious thing. So the L2 norm squared of epsilon plus the L2 norm squared of alpha. Okay, so in this way the moduli space of n vortices gets a metric. One nice thing about it is that this equips to the Riemannian metric. So Riemannian metric. And this Riemannian metric is actually Hermitian with respect to the following almost complex structure. So it maps epsilon alpha to I epsilon Hodge dual of alpha. Okay? So it's obvious that this leaves this invariant, of course, that this is an isometry of this squared norm. It's not quite so obvious that this really preserves tangent vectors, that it maps solutions of this triple to solutions of this triple, but it does. So this equation is left invariant, and these two just swap with one another. Okay, so it's Hermitian, and in fact it turns out it's Kähler, but that's not immediately clear at this point. Okay, so this is good. We've got a natural Riemannian metric, which is summation, and actually it turns out to be Kähler on the moduli space. That's nice and natural, but is it interesting? Well, the answer is yes, it is. For the following reason. So if I look at my moduli space, which is some finite dimensional complex manifold over here, then a point in that corresponds to an n-vortex. And an n-vortex, if you look at it, if you plot its energy density, say, generically looks like n lumps of energy centered roughly at the zeros of the Higgs field. Z1, Z2, Z2. Okay, so that's what a point in the moduli space corresponds to physically. What if I start with an initial velocity vector and solve the geodesic flow with respect to the L2 metric on this moduli space? Well, as I do that, these vortices move around on some curves, and they hit one another and they interact in some complicated way. Okay, so this defines, so the idea is that geodesic flow in Mn defines a vortex dynamics. It gives a rule for saying how these things move around and interact with one another. Okay, well, that's very nice and geometric, but it's rather a strange way to define the dynamics of static solutions of a field theory. If you were going to do physics, a more sort of physically motivated vortex dynamics, how would you define that? Well, what you do is you would extend your line bundle so that it was living not over just space, static space, but over space-time, and give that a Lorentz metric. And then once you've done that, you'd write down the same functional E, I've now rubbed off, except you'd reinterpret it as an action because it's not positive definite anymore, and there'd be some minus signs to take care of this change of signature. And the right way to define dynamics physically would be to say you demand that your fields are critical points of this action functional. In this way you get some coupled nonlinear wave equations, and you could solve the Cauchy problem corresponding to this, the initial date of this geodesic motion. Okay, so this is a completely different way and much more difficult way, I guess, technically, of defining vortex dynamics. But this is physically really the dynamics that you would be interested in. Okay, well, the point is that Nick Manton in 1982 conjectured that the real dynamics, so this one whose definition I wasn't very precise about, but is defined in terms of a Lorentzian extension of your model, that this is approximated, so converges to geodesic motion in Mn at low energy. So if you give your vortices a small amount of kinetic energy. Okay, so it's conjectured by Manton, not as a precise mathematical conjecture, more as a sort of physical principle. It was then formulated very precisely by David Stewart, at least on the plane, and in 1994. So Stewart has proved a precise formulation of this. So he proved it on the plane, but actually his whole argument will go through for a compact surface as well. In fact, it'll just be a lot easier because there are a lot of technical issues to do with non-compactness, which just go away. Okay, so this dynamics is interesting because this geometry is interesting because the geodesic motion has a good physical interpretation. So what can we say about it? So what is known about the L2 metric? Okay, well, in general, it's quite hard to find exact results about this metric. It's even though it's defined quite concretely, it is hard to find explicit formulae and so on. But there are certain limits where you can say interesting things. So, for example, remember we've got this parameter on a compact space anyway, tau. So in the limit where tau goes to infinity, you can ask what happens to the vortices. Okay, so if you fix the zeros of your n vortex and just consider the one parameter family of solutions to the one parameter family of models where tau goes off to infinity, what happens? Well, their total energy diverges and they shrink. They become point-like objects. Okay, so they shrink to sort of point-like things. So if you think about the geodesic motion in that limit, what would you expect on physical grounds? Well, since they're point-like, they shouldn't really interact with one another at all unless they actually hit one another, because there's no non-local structure to them, they're just point-like things. Okay, so just by looking at that, you would expect the metric, so you'd expect the geodesic motion to tend to the independent geodesic motion of n points on sigma, as long as they don't hit one another. Okay? And indeed, this turns out to be true. So this is a theorem of Mundet e Riera from 2010. I mean, I'm a bit hesitant to write this thing up actually because he hasn't published it anywhere, and the only way I know it is because I happened to see him announce it at a talk in the autumn. So this is my memory from September of what he claims to have proved. So you filtered through a few layers there, but I think this is what it says. So if we fix a compact subset in the complement of the coincidence set in Mn. So this is the coincidence set. That is the set on which one or more of the zeros of the Higgs field are equal, right? So remove the coincidence set and then take a compact subset of the open set you've got left. Once you've done that, so we can define there's a natural projection from sigma n to Mn. Remember, this is just a symmetric product. Okay, so there's an obvious projection from here to here. And what he proved is that, so I can pull back, so the complement of the, I can pull back this metric here to here, right? And if I have to normalize it by dividing by tau, then it turns out that this one parameter family of metrics on here converges uniformly on this compact set that I started with to the obvious one. Okay, so it converges uniformly on K, sorry, on the pre-image of K, I mean, of course, to the obvious one, which is just pi times the obvious metric on sigma m. Okay, so let me write that as g sigma m, the product metric on sigma. Okay, so this is saying that this is exactly true. Okay, this physical intuition you have, because these things are shrinking to point particles, that unless they actually hit one another, they should just follow geodesics in the physical space. It turns out to be correct. I guess okay. Of course, this is only approximate. I mean, this is an approximate formula, right? I mean, this metric isn't really equal to this. It just converges to it because tau goes to infinity. Okay, what else can you say? Well, that's on a compact space. In fact, an analogous result has been known for many years on the complex plane. It follows immediately from results of taubes, in fact. So, an analogous result holds on the complex plane. So now on the complex plane, there's no such thing as tau. In tau, you can always set tau to 1 just by a homothency of your surface sigma. And for the complex plane, a homothency is the same as an isometry. Okay, so without loss of generality on the complex plane, you can just set your complex parameter tau to 1. So there is no limit tau goes to infinity. It doesn't really make sense. A better way to think of it, so the analog of tau goes to infinity, well, that really is, you define R to be the minimum vortex separation. Okay, so the minimum of the distances between the zeros of the Higgs field. So let me define that more. Okay, and the analog of the thing shrinking to point particles, now they have a fixed size, they don't shrink, and the analog of them shrinking is to send them a long way from one another. Okay, so then the same intuition holds really. So that they look more and more just like point particles as they get further and further apart from one another. So Taubes proved that an N vortex, when they're well separated from one another, is really just a superposition. You can model it, you can approximate it by a superposition of n one vortices, and you'll get things, you'll get very close to the right solution. The error is of order e to the minus r, where r is the minimum vortex separation. Okay, so just from that and the definition of the L2 metric, it's not hard to convince yourself that the metric has to converge as they go off to infinity to just the obvious Euclidean metric on n copies of C. So I'm being a bit sloppy here. I really mean the pullback of this by the projection from the symmetric, so from Cn to the symmetric product, but let me just write it down. Okay, so that is the flat space analog of Munda e Riera's result, and it's been known for donkey's years. But actually we can do a bit better. So it follows pretty much directly from Taubes' analysis of static n vortices that this must be true, but we can actually, at least conjecturally, write down a formula for the order e to the minus r bit of this correction. So we can write this as an explicit formula order e to the minus r plus an order e to the minus 2r correction. Okay, so the way we do this is to think physically. So if I mean, you can't write down exactly what a single vortex, even on the plane, is, but somehow you can still get a very good idea of what they look like. Okay, so let's just think about what they look like. So let's say I have a single vortex with a zero of the Higgs field there, then its energy is peaked at the zero of the Higgs field. And it turns out if you look at the field, the Higgs field and the connection a long way from the center of the vortex, you can work out what their asymptotic forms are by solving the linearization of the field equations. And it turns out that the asymptotic fields are exactly the same as the fields of a point particle of mass pi with scalar charge q and magnetic dipole moment q. In the linearization of this field theory about its vacuum. Okay, so maybe to a mathematical audience that's a bit off-putting, that statement, but all I'm really saying is if you look at this vortex from a long way away, what it looks exactly like the fields induced in a linear field theory by a point source at the center of the vortex carrying a scalar charge and a magnetic dipole moment. Okay, so on physical grounds, when they're a long way from one another, you would expect that the forces between them approach the forces between these point particles in this linear theory. Okay, well, scalar charges attract one another, and magnetic dipole moments repel one another. And so an immediate consequence of this is that you would expect that static vortices neither attract nor repel. The force is exactly balanced. Okay, so this is sort of the physicist's way of, the physicist's intuition behind the fact that you have this big parameter, this big space of static solutions. It's because these competing forces are cancelling one another. Okay. Of course, this is all formal. There's nothing rigorous about this. Okay, so static vortices, as we already knew, don't exert any force on one another. But when they're in relative motion, because these two forces are mediated by different kinds of fields, there's no reason why the forces have to cancel once they're in relative motion. Okay, so you can compute velocity-dependent. You can compute the velocity-dependent forces between moving point vortices. Okay, so in linear field theory, it's a bit it gets a bit complicated, but you can do the calculation, and what you find is that according to this point particle model, the trajectories of the vortices should move. They should follow GD6, not in the whole of Mn, but in a sort of thickened. So you have to take away a thickened chunk of the coincidence set with respect to the following metric. So what we have is the bit that we know we have to have by Taubes' observation, minus, and then this thing. Okay, where ZRS is the difference between ZR and ZS. Okay, so you can work out these how these point vortices should move, and the point is, it looks very similar to what you would expect the asymptotic metric for on the n vortex moduli space to look like. So this naturally leads one to conjecture. Okay, so this conjecture is due to me and Nick Manson from 2002, that the L2 metric, which I'm calling gamma, I suppose, is this metric here, plus a correction of order e to the minus 2r. Okay, so this is all very formal. I mean, the method I've just sketched for deriving that is very formal indeed. There is an alternative argument which gives the same result, which is slightly less formal, but still not fully rigorous. Okay, so this is certainly not a theorem, but there is quite a lot of evidence in favour of it. Okay, so you can say something about the asymptotic form of this metric when the vortices are either very small on a compact space or when the vortices are very well separated in Euclidean space. What else can you say? Well, the main tool for analysing this metric is something called localization. Okay, so let me try and formulate this reasonably carefully. Okay, so as I said before, there's a natural map from Cartesian products of sigma n times with itself to Mn. Okay, just a projection from this to this modulo Sn, right? On here we have a metric, which is the L2 metric, which I'm calling gamma. I can pull that back to give this a smooth 2 form, but of course it's not going to be a non-degenerate 2 form, so I shouldn't really think of this as being a metric on here. So this is going to be degenerate on the pre-image of the coincidence set. Okay. So what I'm going to show you is how you can get an almost explicit formula for this pulled back metric off the complement of the coincidence set. Okay, so let's remove this. Okay, again. So this has a metric on it. It pulls back to a genuine metric up here. Okay, and what I'm going to show you is a metric for this. Okay. All right. So the formula takes a little bit of setting up. So I won't just launch straight into it. So the point is, given a point, actually I suppose I have to choose a local coordinate. Yeah. Okay. So let's choose a complex coordinate, a local complex coordinate on sigma. Okay. Then given an n tuple of points in sigma to the n, none of them equal to one another, is what that says, then I can define the following quantity. Okay, so associated to that there is an n vortex solution. Okay, phi. Let's take its Higgs field phi. Let's take its length squared with respect to the fiber metric. Let's take the logarithm of that. Okay, so that is a real valued function on my space sigma, except it's not. It has singularities at the zeros, right? Where phi is 0. Okay, so let's pick a 0, one of them, ZR say, and expand, write down a power series expansion for that. So we have a logarithmic singularity to start off with, but then the rest of it is smooth, and we can do a Taylor expansion of it. Okay, so this is the expansion about ZR, so the coefficients will be associated to. Okay. So in this way, I can define these coefficients here, which are complex valued functions from the complement of the coincidence set in sigma n. Okay. Okay, so I've got so the point is that these coefficients, I have R of them, I have one for each one of the zeros, I do an expansion about each one of the zeros, and they depend on which n vortex I'm talking about. So they depend on the parameters Z1 to ZR. Okay, so that's what this says here. Okay, so let's package them together into a 0-1 form. Okay, so that's the thing, that's the bit of setup I had to do in order to write down this formula. Okay. So having done that, if you believe, if you're happy with that, then I can write down a formula for the L2 metric in terms of this 0-1 form B, okay, which is defined on this. Well, actually, it's easier to write down a formula not for the metric but for the Kähler form. So, of course, that's equivalent. Okay, so the following is a theorem of Samuels and Strawn from 1992. And it says the following. So if I consider the pullback by this projection of the Kähler form, then this is precisely pi times the obvious Kähler form on sigma n plus I pi, and I can't help feeling there should be a 2 there, so I'm going to put one in, dV. Okay. So this is very nice, right? This looks like quite an explicit formula. The only problem is, of course, we don't really know what this 0-1 form here is, because it's defined in terms of this unknown Higgs field. On the plus side, however, you can figure out quite a lot about the symmetries and the sort of basic analytic properties of the 0-1 form, and from that you can deduce quite a lot about the metric. Okay, so this is not quite an explicit formula, but on the other hand it's useful. You can get a lot of mileage out of it. So one thing that follows immediately, by the way, is that the metric is scalar. Okay, because this is a manifestly real form. I mean, we defined it by using a real metric. Okay, so a Hermitian metric. So this is manifestly a real form, so it follows that d bar b bar is minus db, from which it follows that that's a closed form, right? Okay, and this is obviously closed, so it follows that the scalar form is closed. Okay, so that's one way to see that it's scalar in a rather more sort of direct and hands-on way than the more elegant stuff. Okay, so what can you get from this? Well, one thing that's allowed SAML to do is make a very detailed study of geodesic motion on the 2-vortex moduli space on the plane. So a 2-vortex corresponds to a monic polynomial of degree 2. Okay, so it decomposes into a product of two planes. This one parameterized just by P1, which is essentially the center of mass of the pair of vortices, so that's flat. This is a flat plane. And this one here, parameterized by P2, that's not flat. So it turns out that you can figure out numerically what its metric looks like. It's a sort of rounded cone. It's asymptotic to a flat cone of deficit angle pi. And the geodesic motion, you can just throw this bit away, it just projects out. And you're really interested in geodesic motion in this rounded cone. Okay? And then the interesting thing, if you haven't seen this before, maybe everyone has, I don't know, is that there are geodesics which go over the top of the cone. So that corresponds to, so P1 is 0, say, that just corresponds to P2 going through the origin. And what that corresponds to physically, if you track what the vortices are doing, you've got two vortices heading straight towards one another. They collide, so that's when, so get rid of that, that's when P2 is 0, and then they fly apart at right angles. Okay? So this is one of the first times, I think this is the first instance where this behavior was noticed. Okay? That you've got these planar solitons, you bang them in, they form a ring, and then they split apart along 90 degrees. This is very characteristic behavior of solitons in 2 dimensions. Okay. Well, what else can I say? I'm running out of time, I guess. So let me be a lot briefer. So one situation in which you can make real explicit progress is the case of vortices on the hyperbolic plane. So vortices on H2. In a special case where you give the hyperbolic plane curvature minus a half, that corresponds to tau being 1. I mean, you could change tau and change kappa. There's a relationship between them. Okay, this case is special. There's something very special about it because the Bogomolny equations, it turns out, are integrable in this case. In fact, you can rewrite them as Liouville equations. So the Bogomolny equations are equivalent to the Liouville equation. And another way of seeing that this, of being tipped off that this is likely to be special, is that actually the Bogomolny equations you can write as a symmetric reduction of Self-Julian-Mills theory as well. Okay, so there's different ways of seeing it, but the Bogomolny equations are integrable. And even better than being integrable, you can integrate them, right? Which is of course not the same thing. So you can actually write down, explicitly the vortex solutions in this case, which means you can actually hope to use this Samuel's formula, which up there, because you know what the vortices are explicitly, you can hope to do these expansions explicitly, compute this form B explicitly, and actually get a formula for the metric. And indeed, this was done by Strawn. in 1992. In fact, this is precisely the context in which he first wrote down this localization formula. Okay. So he computed explicitly the metrics on M1 and M2, but you can go further actually. So this is an observation by myself and Stefan Krusch from last year. So you can define totally geodesic disks in the n plus m moduli space on the hyperbolic plane. So let's just use the Poincare disk model of the hyperbolic plane. So this disk, this two-dimensional submanifold, consists of, you stick m vortices in the middle and arrange n vortices on the vertices of a regular n-gon. So the corresponding polynomial will be z to the m, z to the n minus alpha. Okay, so you can always define this disk for all n and m. It turns out that it's totally geodesic if m is strictly less than n. Okay, so this gives you a whole family of totally geodesic disks sitting inside these moduli spaces. And again, because there's a lot of symmetry, you can actually write down the metric explicitly. So again, we have explicit metrics. Okay, well, there's something a bit interesting about these metrics. I mean, this is really what I'm telling you. There's a nice fact about them, which is we don't really understand. So there's something to explain, which is the following. If you imagine what happens as alpha goes to 1, okay, then the vortices here are the ones that move, right? These are fixed at the origin. These are at the nth roots of alpha. Okay, so as alpha goes to 1, the vortices are moving towards the boundary of hyperbolic space. Okay, so again, there's some notion that they should become non-interacting particles, and the metric, so as alpha goes to 1, so the metric should, and in fact does, converge to the induced metric by m1 to the n. Okay, so you can compute the length of the curve. Forget about this one. Just think about this thing as n independent vortices moving in m1. Okay, in that way you get a sort of embedding of our disk into here, and you can compute the induced metric on the disk. And just on physical grounds, you would expect, and in fact you can calculate it, and it's true, that this would converge to this metric here. Okay, and that metric there is it's a hyperbolic. It's just this is again just a hyperbolic plane with kappa equal to -1/3 pi n. Okay, so all of these disks are asymptotic to this just uniform hyperbolic disk, and that has to be true even without doing a calculation. You could have figured that out. The weird fact is that when m is exactly n-1, so when you have exactly n-1 vortices sitting at the middle, this is actually exact. Okay, so not only is this metric asymptotic to this hyperbolic metric, it's actually exactly equal to the hyperbolic metric. So there are no corrections to the asymptotic form coming from short-range interactions. Okay, so this is a very strange fact, but you can calculate it, and it's true. And it would be nice to know if there's a sort of deep reason for it. Okay, so I've got 5 minutes left, and I guess I should very briefly mention some other stuff by Nick and his student Nuno Romao. Nick Manson and Nuno Romao. Okay, so as we've seen, there's quite a lot of stuff you can get, quite a lot of mileage you can get out of the idea of a limit where the vortices either separate from one another or where they shrink to zero size. Then somehow you can make explicit statements about the form of the metric. What about the opposite? What about the opposite limit, the dissolving limit? So remember, we had the Bradlow bound. That tau had to be bigger than some lower limit, which was 4 pi n over the volume of sigma. Okay? So tau goes to infinity is one limit where they become point-like. What happens when tau tends to 0 from above? The so-called dissolving limit. So now the vortices spread out, and essentially they fill the entire space. Okay? The space is only just big enough to accommodate them. So thinking of them as point particles is going to be completely inappropriate, and one's physical intuition is not so much use. Well, one thing we can certainly say something very concrete about is the dissolved limit. At tau equals tau 0, well, from the second Bogomolny equation, in order to attain the Bogomolny bound now, so the second Bogomolny equation will tell you that the Higgs field has to be 0 everywhere. Okay? Which implies, of course, since the first Bogomolny equation, if you remember, was that, it follows immediately that the first Bogomolny equation holds. Okay, so now in this particular very weird limit, solving the Bogomolny equations, the phi is 0. The first Bogomolny equation is trivial. The second Bogomolny equation just tells you that your connection has constant curvature. Start at that. Okay, so what you're looking for is connections of constant curvature. So Mn equals this moduli space of connections of constant curvature half tau 0. So how can you think about that? Well, once you've got one of them, how do you get all the others? If you have one connection, so this is not unique, of course, so if you've got one connection satisfying that condition, then you can always add anything close to it. But exact forms generate gauge transformations, so you should throw those away, and you should really take things which are closed but L2 orthogonal to the exact things. In other words, you should take harmonic one-forms. So this is a space of harmonic one-forms. Alpha modulo a lattice. So this lattice is the lattice consisting of harmonic one-forms whose associated connections have completely trivial holonomy. Because remember, we still have to mod out by the action of the gauge group. Okay, so we've got rid of some of the gauge group, but we haven't got rid of all of it. Okay, so harmonic one-forms you can think of as being, they're uniquely specified by holomorphic one-forms. Just take the real part of the holomorphic form, you get a harmonic form. And so what we have here is a space, this is a torus, right? So this is complex space CG, where G is the genus, modulo a lattice, call it lambda, and in fact you can identify it as being a torus dual to the Jacobian of sigma. Okay, so that's what the moduli space is, and it turns out it has a natural metric. The L2 metric turns out to be a natural metric on this, defined in terms of the period matrix, the imaginary part of the period matrix. Okay, so that's the situation when the vortices have actually dissolved. What about in the limit where they are dissolving? Okay, I think I can wrap this up in about 3 minutes. Well, in the case of general degree, things are a little bit subtle. So let me just state what's known for the degree 1 moduli space. Okay, so now M1, of course, is just a copy of the Riemann surface sigma itself, and one has a natural map from the Riemann surface into its Jacobian, called the orbital Jacobian map. Okay, and we can equip this space here with, this is just a very trivial flat metric on the dual of this. Let's equip this with the dual of that metric. Okay, then the theorem So this is due to Manton and Ramau, 2010, is that as tau tends to tau 0 from above, the L2 metric on M1 converges to the pullback of this by the Arbor Jacobi map. Okay? So it's equal to this up to corrections of order tau minus tau 0. Okay? So this is a very bizarre result because this metric here, which is defined in terms of this metric here, doesn't depend on the metric on the moduli space at all. Right? And the Arbor Jacobi map also doesn't care about the metric. So somehow in the dissolving limit these things have grown very big and they're living on the whole of the space sigma, and all the local information about the geometry of sigma has been lost completely. So this is weird. Okay? So I should really stop. I just want to mention, without going into any details at all, what else can be done. So Manton and various of his students have computed volumes of the moduli space. That's rather a nice subject. Okay. So even though you can't write down the metrics exactly, it turns out using cohomology and intersection theory and knowing that they're Kähler, you can figure out their volumes exactly. What else? Well, I haven't mentioned anything about non-abelian vortices. So there's the various interesting generalizations of this whole story. One of the most interesting is non-abelian vortices. So where the gauge group is no longer just U1, it's something more non-trivial. So there's the state of play is more fragmentary, but a lot of the theory can be generalized, and there's some very interesting results. So João Baptista just written a very big and I think rather impressive paper on that. Also semi-local vortices, meaning still U1 gauge group, but a section of a higher rank bundle. Your Higgs field is a section of a higher rank bundle. And the other thing which is interesting is adding a Chern-Simons term. So there's a conjecture due to David Tong that if you add a Chern-Simons term and change you change the theory a little bit in other ways as well, then instead of the vortices following geodesics in the moduli space, they follow magnetic geodesics. That is, they follow instead of satisfying the geodesic equation that is equal to 0, they satisfy something involving the the Ricci form. So I shouldn't call it gamma, should I call it X? Yeah. Okay, so they deviate from geodesics, and the deviation, the force that causes the deviation, is governed by the Ricci form, the Ricci curvature of the moduli space. Okay, that's a very interesting dynamics about which not that much is known. So I think there's still an awful lot to figure out about these things. Okay, thank you.
Question?
Yeah.
You talked about estimates on the metric.
Yes.
But does that also extend to the first derivative or two, because you want to compare
Yeah, that's a good point. Yeah.
he's talking about uniform convergence on metrics.
Yeah.
What about the
Being
derivative?
the connection.
Geodesics and curvature depend on that. Geodesics can go off.
Yes, that's true. Yeah. No, I don't think anyone is directly. So you really want estimates on the connection, right? It's the connection that goes.
You need the Sobolev.
Yes, sure. The answer is no. I'm not aware of anyone doing direct estimates. I mean, so this asymptotic formula I had for the metric, I should point out, it's not rigorous, right? So the first thing would be to prove that before one worries about proving more refined things.
You mentioned the vortices on the hyperbolic plane and the fact that the system was integrable due to the fact, if I understood correctly, that they are dimensional reduction of instantons, right? Or that
I mean, you
was-
never actually use that, but yes, it's.
Yeah, because that's the fact which is actually true.
I mean, it's actually the other way around. I mean, historically, what happened was people noticed that this reduction reduces the vortex equations, and the vortex equations on hyperbolic plane can be rewritten as Leville's equation. You can solve Leville's equation,
Okay.
and they went the other way. in fact.
Okay, that's what I was going to say, but actually this fact of dimensional reduction is true also for vortices on the plane and
Yes.
for compact Riemann surfaces. I did actually give another proof using that point of
Okay.
view, relating the moduli space
Uh-huh.
of vortices to moduli space of stable bundles, actually.
Right.
On the product of the Riemann surface by the sphere. In fact, I want to ask you this: the limit, this limit that you refer to, Fratto limit,
Mhm.
has here an interpretation in terms of the volume of this sphere sort of varying, right?
Is that right?
Yeah.
I mean, I don't see that, but yes, I
Oh,
can
I'm
believe
telling
it.
you. I mean,
Yes, okay.
The parameter.
So what happens to the sphere?
Well, is it gets smaller and smaller, right? So
Right.
the parameter is actually encoded in a Kähler metric on the product of the Riemann surface by P1,
Uh-huh.
by CP1,
Yeah.
and so the variations of this parameter correspond to variations of the volume.
Okay.
Right? So I wonder if moduli space of instantons and metrics on those have also been studied, and I don't know if this has an interpretation in relation to that.
Yes, I mean, yeah, there's going to be a dictionary, right? But
Yeah, sure.
transferring, but what I'm not sure how much. I'm not sure it's ever any use. Maybe it is. Maybe it is. Yeah.
Non-abelian vortices have been studied for more than 20 years. On, so I don't know what you're referring that.
Well, so what I'm saying is that the geometry of the modular space of these things
the
is
geometry.
not so well understood, right?
No, certainly.
And Jean Baptiste has just published a
Study the
paper where
geometry.
he's
Okay, very nice.
he's got some very nice, like he has some very interesting volume formulae. So he's computed volumes of these things.
For higher rank.
Yeah, and he's established some regime in which the Samuel's localization type formula can also be written down.
Because there are some cases where, in fact, one knows explicitly what this moduli space is, like in the case of Swan 1.
Right.
Right, the abelian case.
Yes.
Also, in the non-abelian case, you can. There are situations where you can, in fact, say what the manifold is. Explicitly.
Yes.
So I
Yes.
imagine- Okay.
Yeah. So the point of the point of Jean's work is very much the metric, studying the metric. on
No,
those
but
things.
because you know what the space is, you can sort of.
Well, I mean, do you know explicitly what the solutions are? You're saying.
No, not the solution.
Right.
I'm saying what is the moduli space.
Right. Sure.
Right.
Yes. Well, yeah, that's the first thing you need.
I mean, it's sort of non-trivial to get the metric on the space. I mean, even if you know what the modular space of solutions is as a complex manifold,
I understand.
it's not
Yes.
trivial to work out this metric.
I understand, but precisely because what my point is that because you know explicitly what the space is, it's worth pursuing also what the geometry is precisely
Yes.
why you, in this case, you were studying the abelian vortices because you know very well what the space is, the symmetric product of the Riemann surface, and because in general, it's very difficult to know what the moduli space is explicitly, right? I'm saying there are many cases where you know what it is explicitly, and therefore it is really worth studying, right? What is the Riemannian geometry? I don't know if this is what they say.
I think it is. Yeah. Well, that's part of what he's done. He's done other stuff as well. I mean, I don't properly understand the paper.
So my understanding is that this non-abelian vortex case is also integrable if the underlying surface is the hyperbolic plane with this definite value for curves, for the curves, I think. But still, it's not so easy to explicitly find the vortex solutions, or is that known? I mean, you know, in the
From the hyperbolic
non-abelian
plane.
case.
I mean, of course, even if you know the slightly irritating thing is even when you do know exactly what the solutions are, that doesn't mean you can compute the metric exactly.
No.
So, for example, the hyperbolic, the metric on the three vortex moduli space of the hyperbolic plane, you've got no hope of ever writing it down. even though you can write down the solutions exactly. Because if you try and use this Samuel-Strawn formula, you end up having to solve some unbreakable way, and you've got no means of solving it. Okay.